Alright, welcome to this next edition in this series of videos. This is sort of a redo. I had a little bit of a technical problem, so I had to redo this video. And so since I know what's coming, a lot more certain of what's coming, maybe it'll go more efficiently, but maybe not. Let's see what happens, but I'll have to make sure it plays this time.
Electric fields can induce dipoles in insulators. The electrons in insulators are bound to the atoms and to the molecules, unlike conductors where they can freely move. And when I apply an external field, for instance a field in this direction, then even though the molecules or the atoms may be completely spherical, they will become a little bit elongated in the sense that the electrons will spend a little bit more time there than they used to, and so this part becomes negatively charged and this part becomes positively charged.
All right, I think I think that's like I said, that's something I might have believed 3 weeks ago. Trying to understand how things charge, but I think the truth is that it's really just the creation of these ions. You either, if you make an atom bigger, or you make one smaller, what you basically do is change the whole atom into a positive or negative from any direction. It will look more positive than negative, or more negative than positive, because of where you've placed the electrons in relation to the protons. So you bias the atom by ionizing it, by it absorbing an electron or losing an electron, I think is really what's causing the charge effect. It's not the little magnet argument, because you're not really creating a dipole in most cases. You're creating charge on surfaces. And with glass and other insulators, I think it follows just because the charge can be very uneven. You can have positive charge in one location and negative charge in a different location. And they don't have to be proportional or any of that stuff. So I don't think that's true.
And that creates a dipole. I discussed that with you already during the first lecture, because there's something quite remarkable about this. That if you have an insulator, notice the pluses and the minuses indicate neutral atoms, and if now I apply an electric field, which comes down from the top, then you see a slight shift of the electrons. They spend a little bit more time up than down. And what you see now is, you see a layer of negative charge being created at the top, and a layer of positive charge being created at the bottom.
And like I said, I don't think that's happening through the atom. So he's just shifting, and this implies, this whole idea of just shifting the electrons in a direction implies a conductor. It doesn't really imply an insulator. An insulator has trouble communicating these kinds of effects. So to me, it doesn't even work for an insulator, because an insulator wouldn't be able to move whatever you want to call it, distortions easily. The whole point of the insulator is the atoms don't communicate very well.
As a result of induction, we call that also sometimes polarization. You're polarizing, in a way, the electric charge. The substances that do this, we call them dielectrics, and today we'll talk quite a bit about dielectrics. The first part of my lecture is on the web. If you go to 802 web, you will see.
So I guess a way of figuring this out is if I took a piece of glass and I put it in contact with a negative charge, am I guaranteed that I'm going to get a negative charge on the other side of the glass? Will the glass go positive and negative? Or will the outside of the glass perhaps be any charge I make it?
There a document which describes in great detail what I'm going to tell you right now. Suppose we have a plane, capacitor, two planes which I charge with certain potential, and I have on here, say, a charge plus sigma, and here I have a charge minus sigma. I'm going to call this free. You will see very shortly why I call this.
I almost want to speed this part up a little faster, just because this is a little bit redundant, because we already did the 2 plates. He's just doing the same thing. He's just going to slip a piece of glass in between them. So it's separate the plates, increase the voltage, then slip a hunk of glass in that's exactly the same size as the gap, and you get a different effect than you got when you just had the no glass. So it's a little bit redundant. So I think it's, I think we can handle a little speed up.
It's free, and this is minus free. So there's a potential difference between the plate. Charge flows on there. It has an area A, and sigma free is the charge density, how much charge per unit area. So we're going to get an electric field, which runs in this direction, and I call that E free. And the distance between the plates, say, is d. So this is given. I now remove the power supply that I used to give it a certain.
So you probably should call it E conductor and then E insulator, in my opinion. Free and whatever the other word is probably not the best way.
Potential difference. I completely take it away. But that means this charge here is trapped, cannot change. But now I move in a dielectric. I move in one of those substances. And what you're going to see here now, at the top, you're going to see a negative induced layer, and at the bottom, you're going to see a positive induced layer. I call it plus sigma induced, and I call this minus sigma induced. And
all right, so now I would just argue that all he's really doing is changing the gap. So he's just really pushing the plates back together. And so the voltage will drop, the capacitance will go up, and blah, blah, blah. So it'll be just, because he's essentially just eliminated the distance between the two charges by placing something inside that does exactly the same thing in terms of creating the opposite charge. So it's, you know, it's just like making the distance between the two original plates much smaller. And I would argue that the negative charge and the positive charge on the glass, on the dielectric, is imposed from the outside onto the surface, and it doesn't go through the surface. So there is no E field thing.
the reason why I call the other free is to distinguish them from the induced charge. This induced charge, which I have in green, will produce an electric field which is in the opposite direction, and I call that E induced. And clearly E free is of course the surface charge density divided by epsilon 0.
I'd almost call it the imposed charge. He's put two things so close together that the natural effect of like magnets creating magnets, well, the same thing with charge. Once the two plates are that close together, the charge on the one surface is going to tend to charge the opposite on the other surface, in the sense it's going to push one thing one way and push and attract the other way. And so it's going to create exactly the opposite condition on the other surface. And if they're very close together, you could sort of imagine that electrons and even pieces of atom, ions, would be bouncing back and forth between them constantly. The ones bouncing from the high pressure, hitting the surface, losing their pressure, floating back, with less pressure. So you can sort of see that the pressure would be migrating back and forth.
And E induced is the induced surface charge density divided by epsilon 0. And so the net E field is the vectorial sum of the two. So E net, I give it a vector, is E free plus E induced, vectorially added. Since I'm interested, I know the direction already, since I'm interested in magnitudes, therefore the strength of the net E field is going to be the strength of the E field created by the so-called free charge minus the strength of the E field created by the induced charge. Minus because this E vector is down and this one is in the up direction.
So when he's doing the math based on what he presumes to be E vectors of the distance of the material between the material, where I would argue the part that matters is the density of the surfaces, what's on the surfaces. So as I pointed out before, as you bring the surfaces closer, the attractive forces become stronger, and the repulsive also, but I mean the attractive forces would become stronger, meaning that everything would stretch into that space, making it have more space. So it would obviously reduce the pressure because there's more space. And as you push everything back on the line again, as they go further apart, then the charges are further apart, and so now they're not pulling strong enough on each other for the charges to move into this three-dimensional space. So you can sort of understand if something's getting repelled and something's being attracted, that's a much thicker space. And so if you lower the charge and the repulsion, then they're on the same plane, and now when they're on the same plane, their repulsion means you don't have as much density. So there's more density when you have them closer, because you've created more space for the charge to live in.
And so if I now make the assumption that a certain fraction of the free charge is induced, so I make the assumption that sigma induced is some fraction b times sigma free. I just write now an I for induced and an F for free. B is smaller than 1. If b were 0.1, it means that sigma induced would be 10% of sigma free. That's the meaning of b. So clearly, if this is the case, then also E of I must also be b times E of F. You can tell immediately, they're connected. And so now I can write down, for E net, I can also write down E free times 1 minus b. And that 1 minus b now, we call 1 over kappa. I call it 1 over kappa, our book calls it 1 over k. But I'm so used to kappa that I decided to still hold on to kappa. And that k, or that kappa, whichever you want to call it, is called the dielectric constant. It's a dimensionless number. And so I can write down now.
I don't know why they say dimensionless number. It's just a constant that is constant for different materials. So each material has a different k value.
In general, that E, and I drop the word net now. From now on, whenever I write E, throughout this lecture, it's always the net electric field. Take both into account. So you can write down now that E equals the free electric field divided by kappa. Because 1 minus B is 1 over kappa. And so you see, in this experiment that I did in my head, first bringing charge on the plates, certain potential difference, removing the power supply, shoving in the dielectric, that the E field will go down by a factor kappa. Kappa for glass is about 5. That would be a major reduction. I will show you that later. If the electric field goes down in this particular experiment, it is clear that the potential difference between the plates will also go down, because the potential difference between the plates V is always the electric field between the plates times D. And so if this one goes down by a factor of kappa, if I just shove in the dielectric, not changing D, then of course the potential between...
Right. So you could look at it the other way around. You could say that D isn't the same because obviously he's shoving something in that's going to change the difference between the surfaces. And, you know, surfaces are so important in all this physics stuff. It comes up in the two-slit experiment, and it comes up with refractions, internal reflections inside of glass. You know, there's just a ton of surface phenomenon. And it's really underappreciated, in my opinion, in terms of recognizing that transitions between surfaces is where a lot of phenomenon takes place. I just think they missed that obvious kind of fact.
The place is also going down. None of this is so intuitive, but I will demonstrate that later. The question now arises, does Gauss' law still hold? And the answer is yes, of course. Gauss' law will still hold. Gauss' law tells me that the closed surface integral of E dot dA is 1 over epsilon times the sum of all the charges inside my box.
Right, so the point is here is that when he doesn't have it connected to anything and he just has the two plates and he's going to put the glass in, he's not adding any charges. So basically you have the charge you started with and somehow you're redistributing it.
All the charges, the net charges, that must take into account both the induced charge as well as the free charge. And so let me write down here net to remind you that. But Q net is of course Q free plus Q induced. And I want to remind you that this is minus and this was plus. The free charge, positive there, is plus, and at that same plate, if you have your Gaussian surface at the top, you have the negative charge, Q induced. And so therefore, Gauss' law simply means that you have to take both into account. And so therefore, you can write down 1 over epsilon 0 times the sum of Q free. But now you have to make sure that you take the induced charge into account, and therefore you divide the whole thing by kappa. Then you have automatically taken the induced charge into account. So you can amend Gauss' law very easily by this factor of kappa. The dielectric constant is dimensionless, as I mentioned already. It is 1 in vacuum by definition.
So there should be a 5-time degrade in the voltage drop. So the voltage drop won't be all the way down. So when he gets to 10,000 volts and he sticks the glass in, it'll degrade the voltage by 5, but the voltage was increased by 10, so there should still be like 3,000 volts or something, I suppose.
Atmosphere gases typically have dielectric constant just a hair larger than 1. We will most of the time assume that it is 1. Plastic has a dielectric constant of 3, and glass, which is an extremely good insulator, has a dielectric constant of 5.
Yeah, I don't think that's all that good. I think there's other dielectrics that are much higher than that. But anyway, and the dielectric has more to do with whether how easily it charge sticks to it. Essentially, I think. So that constant number goes up, the more ionizable the surface is. You could argue.
If you have an external field that can induce dipoles in molecules, there are substances, however, which themselves are already dipoles, even in the absence of an electric field. If you apply now an external field, these dipoles will start to align along the electric field. We did an experiment once with some grass seeds, perhaps you remember that. And as they align in the direction of the electric field, they will strengthen the induced electric field. On the other hand, because...
All right, so in magnetism, the iron filings line up opposed to the field. So I don't know enough about this grass seed thing and what exactly it's doing to make any comment, but he's basically saying the grass seeds line up with the field. So that would be opposite to what iron filings do. But maybe the grass seeds are a different, I don't know, a different kind of dipole? Nah, wrong word, I think.
Of the temperature of the substance, these dipoles, these molecules which are now dipoles by themselves, through chaotic motion, will try to disalign. Temperature is trying to disalign them. So it is going to be a competition on the one hand between the electric field, which tries to align them, and the temperature, which tries to disalign them. But if the electric field is strong, you can get a substantial amount of alignment.
I guess I would argue that the alignment always seems to be in opposition, so I don't know exactly how that works, frankly. It doesn't sound right to me.
Equivalent dipoles, as a rule, are way stronger than any dipole that you can induce by ordinary means in a laboratory. And so the substances which are natural dipoles, they have a much higher value for kappa, a much higher dielectric constant than the substances that I just discussed, which themselves do not have dipoles. Water is an example, extremely good example. The electrons spend a little bit more time near the oxygen than near the hydrogen, and water has a dielectric constant of 80. That's enormous. And if you go down to lower temperature, if you take ice of minus 40 degrees.
All right, so 80 is much higher than glass, so that means how much charge water can hold. So water's good at holding charge, is essentially the point. And that might just be because it can create these thicker layers that hold more charge. So you could almost imagine that water does that because, yeah, water also water has that transition state of it's vaporish and a lot of other things. So you can imagine that the ions would be on its surface, and it also has that surface tension. So that surface is very different than the water itself. Very different in the sense that obviously there's a molecular difference in how the molecules line up on the surface than how the molecules line up inside the water.
It is even higher. Then the dielectric constant is 100. I'm now going to massage you through 4 demonstrations, 4 experiments. One of them you have already seen. And try to follow them as closely as you can, because if you miss one small step, then you miss perhaps a lot. I have 2 parallel plates which are on that cable, as you have seen last time. And I have here a current meter. I put it an A in there, that means amp meter. And the plates have a certain separation D. I'm going to charge this capacitor up by connecting these ends to a power supply.
So this is just incredibly redundant, and I guess I shouldn't slow it down anymore, but I don't know why he's going through this procedure when he just should say, I'm going to set up the same way as before. Yeah.
And I'm going to connect them to 1500 volts. I'm already going to set my lights because that's where you're going to see it very shortly. I'm going to start off with a distance D, so this is going to be my experiment 1, with a distance D of 1 millimeter. And the voltage, V always means the voltage, the potential difference between the plates is going to be 1500 volts. Forgive me for the 2 V's, I can't help that. This means here the potential difference, and this is the unit in volts. Once I have charged them, I disconnect. This is very important. I disconnect the power supply, for which I write PS. That's it. So the charge is now trapped. As I charge it, as you saw last time, you will see that the ammeter shows a short surge of current. Because as I could charge all the plates, the charge has to go from the power supply.
He's been over this at least 7 times now in the last 2 videos. So we all get this. Plates charging. We all get this. It's just amazing how much time he spends on this.
Apply to the plates, and you will see a short surge of current, which will make the hand of the power of the ammeter, as you will see on the wall there, go to the right side, just briefly, and then come back. This indicates that you charging the plates. And now I'm going to open up the gap. So this is my initial condition. There's no dielectric. And now I'm going to go D to 7 millimeters. And this is what I did last time. The reason why I do it again, because I need this for my next demonstration.
Yeah, but you really don't need to explain it again. So yes, we understand. When you lengthen the gap, the increase in the voltage will be 10 times an increase in the voltage and blah, blah, blah. Well, it'll be 10,000 volts, a 7-time increase.
If I make the distance 7 millimeters, then the charge, which I call now Q3, but it is really the charge on the plates, is not going to change. It is trapped. So there can be no change when I open up the gap. That means the ammeter will do nothing. You will not see any charge flow. Dielectric.
So I don't know why he keeps saying you'll see nothing on the ammeter when the ammeter can't do anything because it's not connected to anything. Can't do anything because it's not connected to anything. If you connected it to ground, you'll see a change. If you connect it to something, but it's not connected to anything, it can't do anything.
Field E is unchanged because E is sigma divided by epsilon 0. If Q3 is not changing, sigma cannot change. So no change in the electric field. But the potential V is now going to go up by a factor of 7 because V equals E times D. E remains constant, D goes up, V has to go up. And this is what I want to show you first, even though you have already seen this. And I need the new conditions for my demonstration that comes afterwards. I'm going from 1500 volts to about 10,000 volts. It goes up by a factor of 7. You're going to see that there. There you see your ammeter. I'm going to, you see this is this propeller voltmeter that we discussed last time, and here you see the plates. They're 1 millimeter apart now, very close. And I'm going to charge the plates. I will count down so you keep your eye on the ammeter. 3, 2, 1, 0, and you saw a current surge. So I charged the capacitor. It is charged now. The voltmeter doesn't show very much, 1500 volts. Maybe it went up a little, but not very much. But now I'm going to increase the gap to 7 millimeters, and look that the ammeter is not doing anything. The charge is trapped, so there is no charge going to the plates. But look what the voltmeter is doing. It's increasing the voltage. It's now approaching almost 10,000 volts, although this is not very quantitative. And now I have a gap of about 7 millimeters, and that's what I wanted. You see that the plates on the left side here are now farther apart than they were before. So that is my demonstration.
So, an awful lot of mush. Already been over this. The thing that would have been interesting is to shove a thick piece of glass in, one that fills the entire space, and then put in a thin piece that only fills 1/10 of the space. And those kind of things would be the one differences I'd like to see. That would be more informative than this redundancy. I'm just being critical. I mean, it's just, this is sort of a performance art, and if a play redos this first scene over 3 times in the play, you'd be like, come on, I already saw that scene. I don't need that again.
Number 1, a repeat of what we did last time. So now comes number 2. So now my initial conditions are that V is now 10 kilovolts. So that's the potential difference between the plates that I have now. And D is now 7 millimeters, and I'm not going to change that. At this moment, kappa is 1. Now...
So technically he is changing the distance, in my opinion. So when he shoves the glass in, he's basically moving the surfaces right into each other. We're back to, a tiny difference in their distance. And so the voltage drops, and the capacitance goes up.
I'm going to insert the dielectric. So I take a piece of glass, and I'll just put it into that gap. Q3 cannot go anywhere, because I have disconnected the power supply. So Q3, no change. If there is no change in the free charge, the ammeter will do nothing. So as I plunge in this...
So Q is really a representation of saying, look, the Q can be in either 2 forms. It's voltage, it's pressure, or the number of charged elements. So you're really just saying how many jelly beans and how big are they, something like that. And so you can make them smaller jelly beans and have more, or you make them big jelly beans and you have less. So Q is almost a term you could almost say is the wattage, and then the voltage is the pressure, and the charge density is the volume.
Dielectric, you will not see any reading on the ammeter. But as we discussed at length now, the electric field, which is the net electric field, will go down by that factor kappa. That's what the whole discussion was all about. That's going to be a factor of 5. And since the potential equals electric field times D, but I keep D at 7 millimeters, I'm not going to change it. If D goes down by a factor kappa, then clearly the potential will also go down by a factor kappa. So now you're going to see the second part, and that is I'm going as...
So I would argue that the electric field didn't go down. What went down was the distance.
It is now, I'm going to plunge in this glass, 7 millimeters thick, put it in there. You expect to see no change on the ammeter, but you expect the voltage different over the plates to go down by a factor of 5. So you will see that the propeller voltmeter will have a smaller deflection. You ready for this? There we go. Now you have a smaller potential difference. There was no current flowing through the plates or from the plates. When I take it...
Yes, no current because it's not connected to anything. The meter can't read anything because it's not connected to anything.
Start again, the potential difference comes back to the 10,000 volts. So that's demonstration number...
And the trick is there's probably charge on that glass as a consequence.
2. Now we go to number 3. But before we go to number 3, I want to ask myself the question, what actually happened with the capacitance when I bring the dielectric between those plates? Well, the capacitance is defined as the free charge divided by the potential difference over the plates. That's the definition of capacitance. And since in this experiment, as you have seen, the voltage went up.
All right, the trick is the glass probably doesn't have any charge on it because it's like when he does that thing where he puts the metal plate on the glass and has to put his finger on it to pull, you know, current through the glass to charge the piece of metal. The conductor doesn't automatically charge. He has to put his finger on it. He has to ground it to charge the metal plate. So the same thing is happening with the glass. Unless there's something to charge it, it doesn't charge. But you know, yeah. So when you pull it out, maybe it doesn't get to keep what it took, so to speak, and it puts it back on the plates.
Down by a factor of kappa, the capacitance goes up by a factor of kappa because Q3 was not changing. And so, since the capacitance, as we derived this last time for plain plate capacitors, I still remember it was the area times epsilon 0 divided by the separation D. Since we now know that with the glass in place, that the capacitance is higher by a factor of kappa, this is now the amendment we have.
So the D is the important thing, right? So as you increase the distance, you make the capacity smaller because you're not creating as much dimensional space in the ions. So if you have ions, positive and negative, and you have more of a field, then the ions are going to move disproportionately. So whether it's positive or negative will depend on which way they move. But the point is they're going to move. And that's creating more space. So that movement in and out creates more space. If they have to stay in a line, then they have less space to occupy, and therefore the capacitance has to go down. I think that's what's happening.
To calculate capacitance, we simply have to multiply now by the dielectric constant of the thin layer that separates the two conductors. It's the layer that has thickness D that is in between the two plates. In our case, I brought in glass.
But that D doesn't represent that small number.
I could write down a few equations now that you can always hold on to in your life, and you can also use them in the two demonstrations that follow. And one is that E, which is always the net E, when I write E is always the net one, equals sigma 3 divided by epsilon 0 times kappa. There comes that kappa that we discussed today. Let's call that equation number 1. The second one is that the potential difference over the plates is always...
So again, I'll just say that these are just proportions. So I'm just saying there's a proportional fact between the distance and how much space the charge is going to occupy. So you could put in the equation the space that the charge is going to occupy, or you could put it in the D. Likewise, for this thing they called the electric field, you could just recognize that the density and the voltage are going to decide what that field is. So you could just put the numbers in for the voltage and the density of the charge, and that'll give you, for example, the Q number. So they're all proportionally related. So these formulas, they've written them to their taste, which is they want to trace this field effect, when I would argue that I would trace the source of the field effect, the cause. So again, we're back to they're so focused on writing an equation that explains the effect, and I would be more focused on writing an equation that explains the cause.
The electric field between the plates times D, because the integral of E dot dl over a certain class is the potential difference. That's not going to change. And then the third one that may come in handy is the one that I have already there. C equals Q3 divided by the potential difference, which in terms of the plate area is A times epsilon 0 divided by D times kappa. Let's call this equation number 3. Now comes my third experiment. In the third demonstration, I am not going to disconnect my power supply. So now, number 3, I start out with 1500 volts, just like we did with number 1. But the power supply will stay in there throughout, never take it.
Okay, he's talking like it's a big, I'm just saying, yeah, okay, we get it. Okay, same exact experiment, you just leave the power supply connected. Got it. That's not a hard concept. I mean, there's all this strangled math, and then on something as simple as just a concept like, yes, I'm going to disconnect or not connect the power supply. It's just so simple, and yet he just has to emphasize it. Like, this is difficult to imagine. How can I imagine you having the wire connected or the wire disconnected? Yeah.
We start with D equals 1 millimeter, just like we did in experiment 1. No glass. I'm going to charge it up, just like I did with number 1. And of course, I will see at the ammeter will show this charge, the surge of current. Now I'm going to increase D to 7 millimeters. Now something very different will happen from what we saw in the first experiment.
Quite obviously. So obviously to have movement of charge, you have to have a difference in the voltage. And any difference, if you have the connected, will move. So if I want to charge a battery, all I have to do is really say the battery's 12 volts and I want to charge it. Well, technically 12.1 volts will charge it, because that 1 volt will just keep piling in there, because if I have 12.1 here and I'm feeding it in, it's just going to keep getting lost. I'm going to keep losing that 1 volt. The same thing's going to happen here. So when he's separating the two plates, the voltage is increasing, but it's draining because it's going to move to the lower pressure. The higher voltage moves to the lower voltage. And so it's just going to be basically trying to charge the power supply. It can't really do. But if it was a battery, for example, the voltage would just go back into the battery. So you'd see the ammeter move, indicating the voltage is going into the battery.
The reason is that the potential difference is going to be fixed, because the power supply is not disconnected. The power supply stays in place. Look now at equation number 2. If that V cannot change, and if I increase D by a factor of 7, now the electric field must come down by a factor of 7. And so now the electric field will come down by that factor of 7, because I go from 1 millimeter to 7 millimeters. So now the electric field changes, because D goes up. In case you...
Well, the electric field won't be changing. What will be happening is the voltage won't be increasing, but the density will be reducing. So, because you're reducing the voltage, you're making a larger distance. So again, you're compressing the space that the things occupy. So you're both going to lower the voltage and lower the capacitance. Both of them are going to be wiped out.
Interested in the capacitance will also go down by a factor of 7, because if you look at this equation,
see, so you're losing both density and pressure.
If I make D go up by a factor of 7, C goes down by a factor of 7. Just look at this, simple as that. So C must also go down by a factor of 7.
So those are the two components of what we might call the watts or the Q or the joules of the system. And so you're basically going to sit there and basically saying that I'm going to lower both the voltage and the amperage, and that lowering that's real energy. It's a real change in the energy of the system, so it has to go back onto the power, so it has to go somewhere if you're going to lower it. So you've given it the capacity to go lower, and it said, fine, I'll go low. And so it's going to give back the energy it took from the power supply, a portion of it.
Nothing to do with dielectric. Nothing. And so Q3 must now also go down by a factor of 7, Because if the potential difference doesn't change, if C goes down by a factor of 7, Q3 must go down by a factor of 7. This goes down by a factor of 7, this doesn't change. So the free charge goes down by a factor of 7. And what does that mean? That means charge will flow from the plates, away from the plates. And so my ammeter will tell me that charge is flowing from the plates, and so that hand there will go to the left. And so as I open up, depending upon how fast I can do that, charge will flow from the plates in the other direction. The charge will flow off the plates, and that current meter will show you every time that I open it a little bit, it will go to this direction. So let's do that first. No dielectric involved. Simply keeping the power supply connected. So I have to go back first to 1 millimeter, which is what I'm doing now. I have here this thin sheet to make sure that I don't short them out. It's about 1 millimeter. And I am going to...
So it'd be interesting if you shove the thin sheet in while it has a 7 millimeter separation, and then shove this thin separation in and see what kind of change that creates.
Now connect 1500 volts and keep it on. And as I charge it, you will see the current meter surge to the right. That always means we charge the plates. So there we go. Did you see it? I didn't see it because I had to concentrate. Did it go like this? Good. So now it's charged. We don't take this connection off. It's connected with the power supply all the time. And now I'm going to open up. And as I'm going to open up, the potential remains the same. So this voltmeter doesn't give a damn. It will stay exactly where it is because 1500 volts remains 1500 volts. But now...
Okay, and it doesn't really remain 1500 volts. So I'm just going to say it again. It really is changing. It's just that all the change is going to basically go back to the power supply. And that's what you're seeing. You're seeing the change in the voltage going back to the power supply. Clearly the plates are higher voltage. They're sending the voltage back. High voltage to low voltage. So it's not frozen voltage in some kind of sense. It's just that you've provided a place for the voltage to go, so it's going to go there. You've provided a voltage difference, 1500, 1501. So every time he turns it, he's adding a little tiny bit of voltage. That little bit, tiny bit of voltage just drains off to the power supply. So the quicker he turns it, yes, the more quickly you'll see it on the ammeter. But technically, you could do it very slowly, just 1 volt at a time, and send 1 volt at a time back to the power supply.
As we open up, we're going to take charge off the plates, and so expect the ammeter to go to the left. Every time that I give it a little jerk, I do it now, it's going to the left. I do it now again, I go to 2 millimeter, go to 3 millimeter, go to 4 millimeter, make it 5 millimeter, 5 millimeter, 6 millimeter, and I finally end up at 7 millimeters. And every time that I made it larger, you saw the end go to the left. Every time I took some charge off. So that is demonstration number 3. Why did I go to 7 millimeters? You've guessed it. Now I want to plunge into dielectric. So my experiment number 4, I start with 1500 volts. I start with V equals 7 millimeters, and I'm not going to change that. There's no dielectric in place, but now I put the dielectric in. So kappa goes in. What now is going to happen? Well, for sure, V is unchanged because it's connected with the power supply.
Yes, so any differential is going to be wiped out, but it's not going to change anyway because all you're going to do is change the distance, which again now is going to change the capacitance. So you're basically just going to create that layer again next to another layer, which means that the layers will be communicating much stronger, which means they'll pull harder on each other, which means they'll create that three-dimensional space again. That's the capacitance. So the voltage is going to remain the same, but the capacitance is going to be restored. That is the density of the charge. Your capacity to add density to the charge will be expanded because you're expanding the differential in space between the ions. The positive and the negative separation is being increased. More space, more opportunity for housing of charge.
But that cannot finish. What happens with Q3? Look at this equation. When I put in the dielectric, I know that the capacitance goes up by a factor of kappa. C will go up by a factor of kappa. If C goes up with a factor of kappa, and if V is not changing, then Q3 must go up by a factor of kappa. Follows immediately from equation 3. So this must go up by a factor of kappa. What does that mean? That charge will flow to the plates. I increase the charge on the plates, and so on.
Right, but he's not increasing, it's not the voltage that's moving, it's, I mean, obviously from its perspective, there would have to be voltage drop as you're increasing the density, right? So if I'm increasing the space, there has to be a bit of a voltage drop, right? Because I'm creating more space and that's less pressure. So there's this little bit of less pressure, so there's more. It says, please, I can take more now of voltage. So now the power supply is going to feed it just the same way as it pushed it back before, and to create the extra space. Because the extra space exists, the the voltage on the plates will drop, and as the voltage drops, the power supply will restore the voltage, and what it's really doing is creating more charge to be able to fill the new space created.
My amp meter will tell me that. And so my amp meter will say, aha, I have to put charge on the plates, and so my amp meter will now do this. And that's what I want to show you. The remarkable thing now is that the electric field E, the net electric field E, will not change. And you may say, you put in a dielectric. Sure, I put in a dielectric, but I kept the potential difference constant, and I kept the D constant. And since V is always E.
Well, the E can't change unless you change the voltage. I mean, the voltage is critical to the E. The field is voltage dependent. So if the voltage is staying the same, your E is kind of stuck.
Times D. If I keep this at 1500 volts, and I keep the 7 millimeters 7 millimeters, then the net electric field cannot change. It's exactly what it was before. That is the reason why Q3 has to change. Think about that. Because you do introduce induced charges on the dielectric. And you have to compensate for that to keep the E field constant. And the only way that nature can compensate for that is to increase the charge on the plates, the free charge. And so that's what I want to show you now, which is the last part.
And I would argue that some of this charge is going on to the piece of glass. And when you pull the glass out, then it'll go back again. Blah, blah, blah.
So I'm going now to put in the dielectric. And what you will see then is that current will flow onto the plates. So the propeller will do nothing. It will sit there, and you will see this one go clunk when I bring in the glass. And then it goes back, of course. There's only a little charge that comes off, and then it will go back. As I plunge it in, you will see charge flowing onto the plates. There we go. You ready for it? 3, 2, 1, 0. And you saw charge flowing onto the plates. When I remove the glass, of course, then the charge goes off the plates again. You see that now.
Right.
I've shown you 4 demonstrations. None of this is into.
So that would be conducive to my argument that the charge is being placed on the glass. It's coming from somewhere. It's being pulled from one place to another, and that's why when you put the glass in, you have to absorb energy, and when you pull it out, you have to give it back.
Not for you, and not for me. Whenever I do these things, I have to very carefully sit down and think what actually is changing and what is not changing. I have no gut feeling for that.
Right. There's lots of experiments to do. So again, there's lots of variations on the experiments, and that's sure what they should concentrate on to dissect exactly what's happening. So, but that's the real trick to this physics thing, is recognizing that there's a whole bunch of experiments, and you sort of have to list them or compile them to understand that you have to fit your model to all those experiments. And I would argue they're not very good at doing that either, which I think is why I think their model isn't complete or fundamentally accurate.
There's not something in me that says, oh yes, of course that's going to happen. Not at all. And I don't expect that from you either. The only advice I have for you, when you're dealing with these cases whereby dielectric goes in, dielectric goes out, plates separate, plates not separate, power supply connected, power supply not connected, approach it in a very cold-blooded way, the real classic MIT way, very cold-blooded. Think about what is not changing, and then pick it up from there and see what the consequences would be.
Yeah, well, I think you can do it just the opposite way. Think about what is changing. But whatever. Obviously, you have to match all the circumstances, and so any variations you can do on the experiment, you'll learn, like I said, put a different size dielectric in, and that'll tell you something about whether this is something to do with the surface distances, the distances between the surfaces, or whether this has something to do with the dielectric itself. And I suppose I would argue that it's going to matter how thick the material is you put in. And if you put a thin material in, you're not going to get the same effect at all. They'll have the same pattern in that you're obviously occupying some space and you're creating extra charge, but it's going to be very much diminished in its effect. Alright, so that's probably enough for this video. I traditionally do it in 2 pieces, and I think the second half of this, gets into the Venn diagram, which is good, and I think it's that other glass experiment, which I think it'll see as another glass experiment. So you could use lots of glass experiments, just trying to understand how glass acquires charge and how it, how you get charge off of it. The fact that it's an insulator, but it's really can't be thought of as something that can't have charge on it. It can have a lot of charge on it, on its surface. It just doesn't transmit the charge through it. It doesn't conduct it. So again, back to his original transparency when he showed the, here I'm gonna change the, the phase of the atoms by moving the pluses and the minuses. It seems kind of obvious that insulators don't work that way, because then they'd be conductors. I think it seems kind of obvious. That has to be wrong. There has to be more to that story. Let's just put it that way. Try to be as fair and gentle as possible. Okay, so I think that's enough. Hopefully it recorded properly and I won't have to do it a third time. So, till next time.